We are now going to start chapter 4, where we will talk about diagonalization of a linear operator. This is a very important concept. It is not true that every linear operator is what we call diagonalizable. So, we will first understand the notion of diagonalizability, and then we will learn criteria for diagonalizability. So, this is going to give us structures of linear operators, and here we will be mainly focusing on linear operators on finite dimensional vector spaces. So, we start with module 1, where we will talk about eigenvalues and eigenvectors of a linear operator first, followed by the characteristic polynomial of a linear operator. Let V be a vector space over a field F and T a linear operator on V. A non-zero vector little v in the vector space V is said to be an eigenvector of T if there exists a scalar lambda in the field F such that T of V is lambda V. This scalar lambda is called the eigenvalue corresponding to the eigenvector V. Let A be an n cross n matrix over a field F. A non-zero vector V in Fn is said to be an eigenvector of A if V is an eigenvector of the linear operator La from Fn to Fn. Recall that the definition of La is that La of x is Ax. So, in other words, Av is lambda V for some lambda in the field F, and the scalar lambda is called the eigenvalue of A corresponding to the eigenvector V. Eigenvectors and eigenvalues are also called characteristic vectors and characteristic values. A simple example: A is the 2 cross 2 matrix whose first row is 1 1 and the second row is 0 1. Let us take this vector V, which is this column matrix xy in R2. Then AV is the vector x plus y y. Therefore, if AV has to be the same as lambda V for some scalar lambda, then the vector x plus y y has to be the same as lambda x y, which gives rise to two linear equations: x plus y is equal to lambda x and y is equal to lambda y. Now, if y is not 0, then by the second equation lambda is 1, and if we put lambda equal to 1 in the first equation, we obtain y is equal to 0, which is a contradiction. Therefore, we cannot have y not 0 at the first place. So, y has to be 0, and if x is not 0, then lambda is 1. Therefore, we have proved that every vector x 0 is an eigenvector and lambda equal to 1 is the only eigenvalue of the matrix A. One more example: it is a rotation operator T pi by 2, that means the rotation in the plane R2 by an angle pi by 2 in the counterclockwise sense. Now, without getting into any calculation, we can say that there is no eigenvalue of this operator in the field of real numbers. Why not? Because if there is an eigenvector v, which has to be a non-zero vector, then it has to satisfy t pi by 2 of v is equal to lambda v for some real number lambda. What does that mean? That t pi by 2 v, which is lambda v, has to sit on the same straight line passing through the origin and v. But that cannot happen because t pi by 2 is the rotation operator. So, t pi by 2 v has to be orthogonal to v. Therefore, the rotation operator t pi by 2 cannot have any real eigenvalue. A theorem: let A be an n cross n matrix over a field F. A scalar lambda in F is an eigenvalue of A if and only if the determinant of the n cross n matrix A minus lambda I n is 0. How do we prove this? Suppose that lambda in F is an eigenvalue of A. By definition, this is true if and only if there exists a non-zero vector v in Fn such that Av is equal to lambda v. Therefore, if we take lambda v on the left hand side, then we obtain Av minus lambda v is equal to 0, and we can write lambda v as lambda In of v, where In denotes the n cross n identity matrix, and we get A minus lambda In multiplied by v is 0 for some non-zero v in Fn. This proves that the matrix A minus lambda In is not invertible, and which is equivalent to saying that the determinant of this matrix A minus lambda In is equal to 0. Therefore, we have a criteria for a scalar to be an eigenvalue of a matrix A, and the criteria is in terms of determinant. This gives rise to the definition of what is called the characteristic polynomial of the matrix A. So, let A be an n cross n matrix over a field F. Look at determinant of the matrix A minus Tin, where In is the n cross n identity matrix and T is being treated as an indeterminate. Then determinant of A minus Tin is going to be a polynomial in T with coefficients from F, and that polynomial is usually denoted by that symbol chi A T, and it is called the characteristic polynomial of A. Therefore, what we have seen just now is that a scalar lambda in F is a eigenvalue of A if and only if chi A of lambda, that is determinant of A minus lambda In, is 0. That means that lambda has to be a root of the characteristic polynomial chi A. Now, we extend this definition for a linear operator on an n-dimensional vector space V. So, suppose that B is an ordered basis for the vector space V, which is a vector space of dimension n over the field F. The characteristic polynomial of T is the characteristic polynomial of the matrix box TB, call it A. In other words, chi A of T is determinant of A minus Tin is the characteristic polynomial of the linear operator T. But then we can ask, what if we take a different basis B for the vector space V? That is the definition of characteristic polynomial of the linear operator T dependent on the choice of basis? The remark says that the characteristic polynomial of a linear operator T does not depend on the choice of the basis for the vector space, because similar matrices have the same characteristic polynomial. Well, it is easy to see, because if two matrices A and B are similar, then we can write B as P A P inverse for some invertible matrix P, and we can see that determinant of A minus Tin and determinant of B minus Tin would be the same if A and B are similar, and therefore the characteristic polynomial of a linear operator T is independent of the choice of basis for the vector space V, and it is usually written as chi T of T, which is determinant of T minus Ti. Here I is the identity operator on V. We have introduced the notions of eigenvalues and eigenvectors of a linear operator, and we have seen that an eigenvalue of a linear operator is the root of a polynomial called the characteristic polynomial. Now, we will see the characteristic polynomial in a more detailed fashion. This indeed contains a lot of information about the linear operator. We will be able to read, for example, the trace and the determinant of an n cross n matrix from its characteristic polynomial. And we have already seen that characteristic polynomial is the same for similar matrices, and that we used when we defined the characteristic polynomial of a linear operator, because the definition used an ordered basis for the vector space V. Let A be an n cross n matrix over the field F. The characteristic polynomial chi AT is a polynomial of degree n with leading coefficient minus 1 to the power n, and A has at most n distinct eigenvalues. Well, this is straightforward from the definition of chi AT. Recall, the definition of chi AT is nothing but determinant of A minus Tin, where In is the n cross n identity matrix, and determinant is indeed a polynomial function, and A is n cross n. and A minus Tin is also an n cross n matrix, and therefore the determinant is a polynomial of degree n, and if we expand it, then we can see that the leading coefficient has to be minus 1 to the power n. So, chi a t being a polynomial of degree n can have at most n distinct roots and therefore n distinct eigenvalues for A. The next theorem says that if T is a linear operator on V and lambda is an eigenvalue of the operator T, then a vector V is an eigenvector of T corresponding to lambda if and only if V is non-zero and V belongs to the kernel of the operator T minus lambda I. Proof: Tv is equal to lambda V for some lambda in the field F if and only if Tv minus lambda V is 0, if and only if T minus lambda I of V is 0, if and only if V belongs to kernel of T minus lambda I. Therefore, it is clear that V is an eigenvector of T corresponding to lambda if and only if V is a non-zero vector and Tv is equal to lambda V, which is the same as saying V belongs to kernel of T minus lambda I. One more theorem. Let lambda 1, lambda 2 and so on lambda n be the eigenvalues, not necessarily distinct, of a matrix A, which is an n cross n matrix over the field F. Then trace of A is equal to the sum of the eigenvalues lambda I, and determinant of A is the product of the eigenvalues lambda I. Recall that trace of A means the sum of the principal diagonal elements of A. So, what is interesting here is that the trace and the determinant of a matrix can be written in terms of its eigenvalues. How to prove this statement? Well, the characteristic polynomial of A is chi a t, which by definition is determinant of A minus Tin, and we know that lambda is an eigenvalue of A if and only if chi a lambda is 0. That means an eigenvalue is a root of the characteristic polynomial, and therefore lambda I minus t has to be a factor of the characteristic polynomial, and lambda 1 to lambda n are the all eigenvalues of A. Therefore, this has to be the factorization of the characteristic polynomial chi a t, that is product of lambda I minus t. Now, here chi a of 0 has to be determinant of A, that is clear, but chi a of 0 is nothing but the constant term, and it follows that it has to be the product of the eigenvalues. And similarly, if we follow the coefficients closely, then we will see that trace of A is nothing but the sum of the eigenvalues. Let us look at the example of the rotation operator once again, T pi by 2. that is rotation by an angle pi by 2 in the counterclockwise sense in the real plane R2. If we choose the standard basis B of R2, then the matrix representation for T pi by 2 would be the 2 cross 2 matrix with first row 0 minus 1 and the second row 1 0. Therefore, the characteristic polynomial of T is chi T of T is determinant of T minus Ti, that is determinant of the matrix minus T I 2, that is the 2 cross 2 identity matrix. So, it is going to be determinant of minus T minus 1 in the first row and 1 minus T in the second row, and the determinant is going to be T square plus 1. But we know that T square plus 1 has no root in R. Therefore, the operator T pi by 2 has no real eigenvalue. So, it is not true that a real matrix has to have a real eigenvalue. In fact, this very important example of rotation operator is one such. In general, let us consider the rotation operator T theta, that is rotation by an angle theta in the real plane R2, where theta is bigger than 0 and less than pi. Then the characteristic polynomial is chi T theta T, that is determinant of T theta minus Ti. We know the matrix representation of T theta with respect to the standard basis. It is cosine theta minus sine theta in the first row and sine theta cosine theta in the second row. So, the characteristic polynomial will be determinant of cosine theta minus T minus sine theta in the first row and sine theta cosine theta minus T in the second row, and the determinant is T square minus 2 cosine theta T plus 1. If you look at the discriminant of this polynomial, then it is 4 cos square theta minus 4, which is negative if theta is in between 0 and pi, which shows that the characteristic polynomial has no real root, and therefore, the rotation operator T theta has no real eigenvalue if theta is in between 0 and pi. Let us look at one more example. Let R2x denote the vector space of all polynomials of degree at most 2 with real coefficients. Consider the linear operator T, which is defined as T of fx is equal to f dash x, where f dash x denotes the usual derivative of the polynomial fx. So, this is the usual differential operator. Look at the standard basis B consisting of the vectors 1 x and x square. Then the matrix representation of the operator T with respect to this choice of basis is this 3 cross 3 matrix with first row 0 1 0, second row 0 0 2 and the third row 0 0 0. Well, how do we get this matrix? The first column is the image of the first standard basis vector, that is T of 1, but T of 1 is the derivative of the constant polynomial, that is 0. So, we get the 0 vector in the first column. Then the second column would come from T of x, that is the derivative of x, that is 1. So, if we write 1 in terms of 1x and x square, we get 1 0 0 as the coefficients. That is what you see over there in the second column, and then T of x square, which is 2x, that is the derivative of x square. So, that written in terms of 1 and x square gives us 0 2 0 in the third column. Then the characteristic polynomial of t is chi t of t, that is determinant of A minus t I3. I3 of course stands for 3 cross 3 identity matrix, and then it is determinant of this matrix whose first row is minus t 1 0, second row is 0 minus t 2, and the third row is 0 0 minus t, and the determinant is going to be minus t cube. Therefore, lambda equal to 0 is the only eigenvalue of t. So, we have a 3 cross 3 matrix with only one distinct eigenvalue, and that is 0. What are the eigenvectors for this operator? So, let f in R2x be an eigenvector of the operator t. That means t of f must be 0, but t of f is f dash. Therefore, eigenvectors of t are precisely all those polynomials f whose derivative is 0. That means all non-zero constant polynomials, and they are the eigenvectors of t. Now, we observe this interesting phenomena that if a matrix is one of the following three types, that is diagonal or upper triangular or lower triangular, then the eigenvalues of A are precisely the diagonal entries of the matrix. This is very easy to see because in all these cases the characteristic polynomial is the product of A I minus t, product over I equal to 1 to n, where A11, A22 and so on ANN are the diagonal entries of A. Therefore, it is clear that the diagonal entries are nothing but the eigenvalues of A. Now, what is interesting is that every n cross n matrix with complex entries is similar to an upper triangular matrix over the field of complex numbers. This can be proved, but it is not true that every matrix is similar to a diagonal matrix even over the field of complex numbers. This is what will be studied in the subsequent modules, and we will learn criteria for diagonalizability of matrices. We have now introduced enough concepts to talk about diagonalization of a linear operator. This will be taken up in the next module, where we will first learn the definition of diagonalizability, and then we will see that with the help of eigenvalues and eigenvectors, we will be able to derive criteria for diagonalizability of linear operators and matrices.